Hey, howdy folks, it's Virtual Schmied here. Today we're going to dive into part 1 of nuclear chemistry, one of my favorite topics, lots of interesting things to discuss with nuclear chemistry and radiation. You can see our essential question there on screen. We just want to know, what is radioactivity, why does it occur, why is going to be a big one there, and why is it important, why do we care, and I'll have a couple examples of that. On the next slide, you can see our learning targets. If these aren't in your notes already, please copy down the essential question and the 2 learning targets that I have here in yellow. If you would please copy those down. The other 2 learning targets we're going to explain in part 2 of this nuclear chemistry. Okay, so radioactivity is a real-world problem, not always a problem, and that's what we're going to talk about next. So one place that radioactivity is a huge problem, especially in Colorado, is from radon gas. Radon gas comes from decaying uranium in the ground. So we have a lot of uranium underneath us in Colorado, not necessarily in big concentrated deposits that are good enough to mine, say in case we wanted to get uranium for nuclear power plants, but there is a lot of uranium scattered throughout the ground in Colorado, and as that uranium decays, one thing that it turns into as it decays is radon. Radon's a big problem because it's a gas. Unlike uranium that stays in the ground, radon gas can get into your home through a lot of different places, and you can kind of see in that diagram there. It'll get into cracks into your foundation. It can come through fittings in the groundwater. The point is, radon can get into your home into a lot of ways. You can get radon test kits for your home. It's a really common thing in Colorado for new home buyers to have the house that they are buying tested for radon to see if it needs to be mitigated. They'll put pumps in the basement that take that gas and pump to the outside where it's not a problem for human health. The bigger problem with radon, as you probably have already guessed, is that it's radioactive. Not a big deal until I get radon in my lungs, which I probably have some radon in my lungs right now, simply because it's kind of everywhere. Probably not much, but it is everywhere. So if you breathe it in and it decays inside your lungs, that can greatly increase your risk of lung cancer, on par with sometimes smoking multiple packs of cigarettes a day, depending on how much radon you're breathing in and how often you're breathing in that radon. So that's radon. Radon is a big problem and a big negative part of atoms being radioactive, but there's other things in our life that involve radioactivity, some good things. So one example is a smoke detector. So you can kind of see a diagram here of how a smoke detector sort of works on the inside. And what they have is a really tiny amount of radioactive material. A lot of times that radioactive material is americium, is how that's pronounced. And that is a completely man-made element that we make specifically for this purpose and for other purposes in like medicine and things. But that americium source is always decaying a little bit and releasing one type of radiation called an alpha particle. Alpha particles aren't very harmful, but they can be detected. So what happens is this americium source shoots out alpha particles. They go through the little hole there, and they go through there, and they're detected on the other side by a metal plate over there. And a circuit is completed. It goes from the alpha particle, negative to positive, and a battery powers it. So as long as your smoke detector is detecting alpha particles, it knows that there's nothing in the chamber here that's going to be blocking those alpha particles out of the way. However, if smoke gets into the detector and blocks off that radiation, and this alpha particle is blocked right there by a smoke particle or right there by a smoke particle, then the detector knows, hey, I'm not detecting the alpha radiation anymore. Something must be blocking that, and the smoke detector assumes that it's smoke or some kind of particle in the way, and your smoke alarm will start to go off. So that's another place that we see radioactivity in our world, is in our smoke detectors, which ultimately help protect us. All right, so let's zoom way in to see what's going on in the nucleus, in a specific one nucleus, not a bunch of uranium, but just one uranium atom. So there's 2 forces going on in the nucleus. There's the electrostatic force, which sounds like a big fancy word, but let's break it down. Electrode just being, well, electricity, charges, positive or negative. Static just meaning that electricity isn't flowing. So electrostatic just being that protons are positively charged, and they're always positively charged. They don't change. And because protons are positively charged, they don't really like to be near each other. You can experience this with magnets, and you probably have. If you take the opposite ends of two magnets and try to put them near each other, they want to repel. Like charges repel. Positive and positive are going to push each other apart. That's a problem if you want a nucleus, because a nucleus is at least half protons, or almost half protons. We'll talk about exact proportions in a little bit. So we have to overcome that electrostatic force with what is called the nuclear force. The nuclear force is a little bit mysterious. It gets definitely into quantum mechanics as far as how it works. But here is the ultimate thing of what it does. It's an attractive force between all protons and neutrons as well. So because it's an attractive force between protons and neutrons. Neutrons become really important for holding a nucleus together. One analogy that you can use is to sort of think of the nuclear force or neutrons sort of like a glue holding the nucleus together. Protons want to push it all apart. The nuclear force wants to glue all those things together. And like glue, the nuclear force doesn't really work unless you get things very, 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 very close together. In the case of like actual glue, you got to get two things to touch to glue them together. But the nuclear force, you don't have to get things to touch exactly, but you have to get protons and neutrons really close together for the nuclear force to be stronger than the electrostatic force. And that's why I specify here the nuclear force is much stronger than the electrostatic repulsion at very small distances. Very small distances like what we have inside a nucleus. So if a nucleus has too few neutrons, meaning it doesn't have enough glue to hold that together, those protons are going to push each other away and that atom is going to decay. Whether or not it decays in a form of dangerous radiation or a form of less harmful radiation depends on the atom, but either way, if it doesn't have enough neutrons, it's going to decay, it's radioactive. What is a little bit counterintuitive is that if a nucleus has too many, that should say neutrons, not protons. If a nucleus has too many neutrons, it will also decay. You can sort of think of like the extra neutrons as squeezing too hard to hold that nucleus together, and it's still unstable. So we have to strike just the right balance in the nucleus of enough neutrons to get that nuclear force to hold the nucleus together stably. But if there's too few or too many neutrons, that atom is not stable, that nucleus is going to decay, and we get some form of radiation out of it. So if a nucleus is unstable, it may undergo decay for different reasons, and we're going to call that radioactivity. We'll talk a lot more about the different forms of radiation. The three big ones that we're going to talk about are alpha particles, beta particles, and gamma waves. Gamma is not actually a particle. Excuse me. So a nucleus that decays is going to release some different type of radiation, but if a nucleus is unstable, it is going to decay. We can't always predict when, but we can predict that it will happen. Okay, let's get into talking about the band of stability here. So the band of stability is the graph that you kind of see on the right side there, and I'll jump into an explanation for it in a little bit here. But what it shows us is the number of protons, and I'll move my head so you can actually see that. The number of protons here on the x-axis, and the number of neutrons there on the y-axis. And we're comparing in a nucleus the number of protons to the number of neutrons. And the dotted line there in purple, that is the space where nuclei are stable, and we call that the band of stability. And notice the band of stability sort of has a curve as it goes up. It looks like it starts linear, but then it starts to curve upwards, and there's an important reason for that. So let's talk about the bottom of the band of stability, where nuclei tend to be really small. These are a lot of the elements that we're most familiar with. Things like carbon, oxygen, hydrogen, nitrogen fall under the category of small nuclei. And they have about a 1-to-1 ratio of protons to neutrons up until about calcium is where we start to get more neutrons. The example I'm going to use is potassium-39 that has 19 protons and 20 neutrons, about a 1-to-1 ratio. However, as nuclei start to get larger, we know that they get more protons. That's why they get bigger. So as it climbs in the size of the nucleus, those extra protons repel each other more and more and more. Every proton you add adds to the repulsion, and it starts to be that you need more neutrons to act like the glue to overcome the repulsion of those positively charged nuclei. So an example of a medium-sized nucleus, still large, would be something like silver 107 that has 47 protons but 60 neutrons. It's those 47 protons that cause it to need those extra little bit of neutrons. When you get to really, really big nuclei, above atomic number 82, anything above atomic number 82 is too big for the nuclear force to hold it together. Any atom above 82 is radioactive, whether it's natural or man-made, and there are both types above 82. So the example of a very large nucleus would be something like uranium-238. There is no form of stable uranium. Uranium-238 is the most common form with 92 protons and 146 neutrons. But even all those neutrons still can't hold any uranium atom together. All uranium is radioactive. Okay, a little bit more about the band of stability. I'm going to move my face again. If we wanted to do just a nice definition for ourselves, it would be this. So on a graph comparing protons and neutrons, the band of stability is the small band, and it is kind of narrow, where nuclei are stable and can exist without having to worry about being radioactive. Outside that band of stability, nuclei are radioactive. On this graph here that I'm showing, only the black dots are the band of stability here, and you can see the black dots very, very narrowly in here, and they stop right at 82 right there. Everything above 82 is unstable, but in this little band that I've outlined, that's where atoms tend to be stable. This graph also shows the different types of decay that can occur, and I think that is a good spot to stop our video for today, because we are going to talk more about the different types of radiation that are released from atoms when they are unstable. So I think that's going to be it for part 1 of nuclear chemistry. Virtual Schmied, out.